Hi everyone, thank you for tuning in. My name is Roy Tel, and this talk is titled Super Fast Derandomization from Very Hard Functions, and it's based on a joint work with Li Chen from MIT. And the plan for today is first to give some background, then present our results, then give just a taste of our techniques, and then mention where we can go from here. So let's go back to the beginning to the definition of BPP from the 70s. When BPP was defined originally, it was immediately, right off the bat, conjectured to sort of equal P. The original paper already states that the author believes that only speed up for infinitely many inputs can be achieved using randomness. But actually, if you look at the paper closely, you can see that it raises a much stronger conjecture. It says that for every function computable in probabilistic time t, you can simulate it on infinitely many inputs in deterministic time O of t, so with just a linear overhead, which is a crazily strong conjecture. And it's been many decades since, and in those decades, we developed the theory of hardness to randomness, which says that under strong circuit lower bounds, we get the randomization results. So specifically, we fix functions computable in exponential time. We say, okay, if there's a function in exponential time that's hard for circuits of a certain size, then we get the randomization with a corresponding running time. So if we start with weak lower bounds, a function in exponential time that's hard, say, for polynomial size circuits, then we get a sub-exponential time derandomization. And if we strengthen the lower bound, we take a function that's hard for larger circuits, we get a faster derandomization. And the extremal point of this hardness to randomness trade-off is the textbook result, which we all know of in Pagliazzo and Wigderson from the late 90s, which says that if there's a function in exponential time 2 to the n, that's hard for circuits of small exponential size, say 2 to the n over 100, then BPP equals P. Or in other words, then probabilistic time t can be simulated in deterministic time polynomial in t. So it's t to the O of 1, where this O of 1 might hide some very large constant, but it's a constant. We can efficiently simulate randomness with a polynomial overhead. And this is the standard textbook result that has been prominent since. Now, very recently in last Fox, Dean Doron, Dana Moshkovitz, Justin O, and David Zuckerman asked the following natural question. Can we go faster? Can we prove that probabilistic time t can be simulated in deterministic time t to the c for some small constant c, some fixed constant that we can control? Now, these classical results, like the Pagliazzo-Wigderson result, they don't have a crazy blow-up. C won't be 1,000,000 if we take a strong circuit lower bound assumption. So if we take the strongest lower bound assumption, maybe we get something like C equals 10. But the difference between a polynomial overhead with C that equals 10 and a polynomial overhead which is just, say, cubic, C equals 3, is substantial. It's very meaningful. And it's especially meaningful when T is large, when we want to de-randomize algorithms that run in large running time, where something like C equals 10 could already make the running time be trivial. And also for a polynomial time T, there's a difference between simulating it with a large polynomial overhead and simulating it with a small polynomial overhead. That's obvious. So the main result of Doron et al. From last Fox was that probabilistic time T can be simulated in time essentially quadratic, T to the 2 plus epsilon. So derandomization with quadratic overhead might be possible, and it's possible under the following hardness assumption. There's a function in exponential time that's hard for very large circuits, circuits of size 2 to the 0.99n, so it's almost 2 to the n, but slightly less. But these aren't normal circuits. We need to assume hardness for Merlin-Arthur circuits. So these are circuits that also get a proof for every input and are able to use randomness to verify that proof. So this is a very strong model. So it's a strong assumption that we need to make to get this derandomization with quadratic overhead. And let's compare this with the classical Pagliazzo-Wigderson result. So they managed to reduce the derandomization overhead from this large unspecified constant to just 2, which is great. And we need to assume a stronger hardness assumption. Like instead of exponential time hard for size 2 to the 0.01 n, we need to assume hardness for larger circuits, and we need to assume that the hardness holds even for circuits of the Merlin-Arthur type. These are strong circuits. So what are the takeaways? First, Doran et al. Showed that this super fast randomization might be possible under assumptions. Secondly, it raises the very natural question of, okay, can we do better than quadratic? Can we get to almost no overhead? And thirdly, the assumption of the paper of Doran et al., this hardness assumption is untested and we don't really understand it well. Intuitively, it seems too strong. So we need stronger theoretical foundations for this super fast randomization. At the very least, maybe we get several different assumptions, or maybe we get more standard assumptions. So what are our contributions? What do we show in this paper? Well, these are the Impagliazzo-Wigderson result and the Doran et al. Result, with the derandomization overhead of poly t and of essentially t squared. Our main result is a conditional derandomization, where I'll discuss the hardness assumption in a second, where the derandomization overhead is basically n times t, where n is the input length. So instead of t squared, we get n times t. Now this is essentially the same for, say, linear time probabilistic algorithms. But when t grows to be maybe a large polynomial or even super polynomial, then this is significantly faster than t squared. So this is a very fast randomization. And we optimize this a little bit. As you can see, there's a 1 plus epsilon factor here on the t. For sub-exponential t, we can transfer this 1 plus epsilon from the t to the n. But it's again derandomization with overhead n times t. And we'll show a conditional result saying that this might be essentially optimal. So we can't get rid of this. However, we're able to show that we can de-randomize probabilistic algorithms faster if we're willing to settle for an average case randomization. So for average case randomization in a polynomial t, we show that we can de-randomize probabilistic algorithms with basically no overhead at all on average. So the overhead is n to the epsilon, where epsilon can be arbitrarily smaller. And what assumptions do we need for this magic? Well, we assume one-way functions, so as standard as it gets, and we assume something that I'll call a non-uniformly strong time hierarchy, which I'll present now. And I will claim that this is not only necessary for such derandomization, but it's also the natural scale-up of classical assumptions. So let's look at exactly which assumption we'll need. So the classical hypothesis, say in Impagliazzo-Wigderson, is that exponential time is hard for circuits of slightly smaller exponential size. So time 2 to the n is hard for non-uniform circuits of size 2 to the 0.01 n. And what it intuitively means is that non-uniformity isn't enough to just speed up all algorithms. And our assumption is precisely that, only scaled up. We will assume that time 2 to the kn, where think of k as a large constant. So this is a larger running time, 2 to the kn, is hard for time 2 to the 0.99 kn, so there's just a tiny gap between 2 to the kn and 2 to the 0.99 kn, where the faster algorithm is given a near maximal amount of advice. So it's just like the previous assumptions, only scaled up, saying that non-uniform advice, even the near maximal one, 2 to the 0.99 n, cannot speed up all algorithms, where the speed up now happens both in this regime of 2 to the kn instead of 2 to the n, and the gap is very small. It's not 2 to the n versus 2 to the 0.01 n. The gap is like 2 to kn versus something slightly smaller than that. And this is what we call the non-uniformly strong time hierarchy, because it's just like the standard time hierarchy, only when the smaller class is also given a near maximal amount of advice. So let's now formally state what we prove. Assume that one-way functions exist. Then for every epsilon, this will be our speed up, t to the 1 plus epsilon. There exists a delta, this will be in our hypothesis, such that for every time t and a corresponding constant k, probabilistic time t can be simulated in deterministic time n times t to the 1 plus epsilon, conditioned on this non-uniformly strong time hierarchy, which says that time 2 to the kn is hard for time 2 to the k minus delta n, with 2 to the 1 minus delta n bits of non-uniform advice. This is just what I promised, only fleshed out in some more detail. And the assumption that's highlighted in bold on the bottom is actually a necessary assumption for this randomization when using the standard approach of PRGs. So basically, when using PRGs, this assumption is as good as we can hope for. And the only quote-unquote unnecessary assumption here is the standard one of one-way functions. The second theorem is the optimization, where we move the 1 plus epsilon from t to n. So we need to assume that sub-exponentially strong one-way functions exist, but other than that, I won't go in depth because the assumptions are essentially the same. Just it's more complicated to state, but it's precisely the same intuitively in the sense of what it means. The conclusion here is that time t can be simulated, probabilistic time t can be simulated in deterministic time n to the 1 plus epsilon times t. Okay, good. So now comes the question of whether or not this multiplicative overhead of n is necessary. And recall that textbook non-uniform derandomization, like BPP is contained in P over poly, the non-explicit derandomization has precisely this overhead, the multiplicative overhead of n. And under a suitable assumption, we show that it's necessary. For worst-case derandomization, we can't get around this. We must pay this multiplicative overhead of n, which says that our derandomization time was essentially optimal. And the assumption that we need is called sharp n-seth, which says that we can't count the solutions of a given k-sat formula in non-deterministic time 2 to the 1 minus epsilon n, and assuming that k is sufficiently large. And what I want you to remember about this assumption is that it's a strong exponential time hypothesis type of assumption, but it's for counting. So it's an assumption that we don't understand very well. There's no strong reason to believe that it's true or false at this point, but it's a natural and plausible one. And now we come to the last result. I just told you that we're able to get a randomization with the multiplicative overhead of n, and that conditionally it's optimal. What we show here is that if we're willing to settle on the randomization that works on average, we can get rid of the overhead almost completely. So again, assume one-way functions, and assume basically you don't have to parse this. Assume the same assumption as the first theorem. Only the parameters are slightly different. It will be a slightly weird time bound, but exactly the same type of hypothesis. So under this hypothesis, we show that probabilistic time t can be simulated in deterministic time n to the epsilon for an arbitrarily small epsilon times t on average, where on average means with respect to all t times sampleable distributions. So it's not just a uniform distribution, it's every distribution that you can sample in time t, and with a negligible error. And in fact, for every language in probabilistic time t, there's one algorithm that looks correct to all t times sampleable distributions. And let me just mention a few extra goodies in the paper before we move on to the techniques. We show an easy, high-level way to bypass something that was thought of as a barrier, and it looked very formidable, but it actually can be bypassed using a high-level insight. And we show how to simplify and extend the original work of Doron et al. To get basically the randomization with overhead that you want, like any overhead that you want, like 1, 2, 3, 4 plus epsilon from a corresponding assumption. So this means that superfast randomization is robust. You play a little with the assumption and you get what you pay for in the conclusion. And we show a general way to simplify a well-known paradigm for constructing PRGs. There's this classic paradigm that's called extract from a pseudo-entropic stream. This is a way to construct PRGs. And we show that it's a special case of a strategy that's very easy to analyze, like easier than the classical way. And it involves a non-standard reduction to something called quantified randomization. I want to give you now a taste of our techniques, where really it will be just one technical observation that I'd like you to remember, because this single technical observation is the pivotal one that paves the way to our results. So look at the classical approach for doing the randomization using PRGs. So there's a PRG G that gets a small seed of length L of n, and it maps it to a large string of length T of n that fools all distinguishers and that can be used for the randomization. We will enumerate over all seeds instead of choosing a random T-bit string. And the textbook approach to do this yields a formidable looking barrier, something that seems very hard to get across. Specifically, the textbook approach is to model distinguishers as non-uniform circuits of size t, because these circuits represent the probabilistic algorithm together with an arbitrary input, which is thought of as a non-uniform advice. So we want to fool, in the textbook approach, all circuits of size t. And it's not difficult to show that a PRG for this distinguisher class requires a seed of length log t inherently. And this thing yields derandomization in time t squared, because we need to go over all seeds. So it's time 2 to the log t, essentially time t. And for each seed, we will evaluate the original t time algorithm, which is again takes time t. So t times t is t squared, and we don't know how to get around this. How can we get the randomization in time less than t squared if we need to go over all the seeds? And the pivotal observation is this. Look at this distinguisher and ask yourself, who is it exactly? So for any fixed language in probabilistic time t, what we ask is whether or not the probabilistic machine that decides the language behaves the same on the output set of the PRG and on a uniformly chosen random string for all inputs. And the point is that we consider all inputs here, but we don't need to model this as an arbitrary non-uniform advice of length t, because the distinguisher is just a machine with an arbitrary input x of length n. So the non-uniform advice is much shorter than the running time. Instead of considering a non-uniform circuit of size t, it suffices to consider a distinguisher that is a time t machine with n bits of non-uniformity. And that's it. That's the way to get around the barrier. Why does this help us? Well, the non-uniformity is small, so what we want to fool is t-time algorithms with n bits of non-uniform advice. And there exists a non-explicit PRG with seed length that is log n instead of log t. The seed length is logarithmic in the non-uniformity. And going over all seeds takes time n, and this opens the door to derandomization in time n times t instead of t squared. That's it. And our job in the paper, which is what we do, is to show that under suitable assumptions, we can make this PRG an explicit one, which is exactly the proof that underlies our main results. Okay, so where do we go from here? What's the meaning of our result and where do we go next? Well, first, the key takeaways. There's an emerging plausible scenario in which the world that we live in is a world in which probabilistic time t and deterministic time t are almost the same. For example, for a polynomial t, there's a likely time gap between the two, multiplicative in n, but for a super polynomial t, or when we consider an average case simulation, the time gap is just t to the epsilon, which is barely noticeable. And this is something that we should start internalizing and considering because it's likely that we live in such a world. And in this case, we can say that there's almost a free lunch setting in simulating randomness for decision problems and for search problems. Our randomization here is simple algorithmically. It also solves search problems because we use a PRG. It does look like a free lunch. And this kind of thing also allows us, for example, to de-randomize algorithms that run, the probabilistic algorithms that run in time slightly better than a brute force algorithm. because our derandomization incurs basically no overhead. Deterministic time and probabilistic time might be almost equal, at least for large T or on average. And lastly, on the converse, lower bounds for probabilistic time will imply lower bounds for deterministic time will imply lower bounds for probabilistic time. Again, because the two are almost the same. Okay, and I'd like to note that in an upcoming work, which is again with Li Jie-Chen, and it's under preparation, it will be published very soon, we show an average case derandomization with the same time overhead, n to the epsilon times t, but we show it first from fully uniform assumptions instead of from circuit lower bounds. And secondly, we show that the derandomization succeeds with respect to all polynomial time sampleable distributions. And like informally, what we get here is under uniform assumptions, randomness is indistinguishable from useless for decision problems and natural search problems, because we can simulate it with basically no overhead and such that no polynomial time algorithm can spot the difference with non-negligible probability. Let me just mention a sample of open questions, but there are a ton. Like superfast randomization is a new area to explore, for which we don't yet have a sufficiently strong theoretical basis. So first, is the multiplicative overhead of n optimal? We show that it is optimal under sharp n-set, but can we show anything without sharp n-set under other more well-studied or standard assumptions? Secondly, our superfast randomization requires crypto. It requires one-way functions. Can we show it only from classical hypothesis? No crypto and no hardness for Merlin-Arthur circuits or for non-deterministic circuits. Just hardness of like time 2 to the kn versus time slightly smaller than that with a lot of advice. And like as a side note, let me say that this question boils down to a well-known challenge called bypassing the hybrid argument barrier. And as another sample open question, can we show a super fast search to decision reduction for the randomization? So as I said, our randomization already solves search problems because we use PRGs. And we but if you were able to show the superfast randomization that does not use PRGs, can you show that we are able to solve search problems without a big overhead, like approximately in the same running time? This is a generic great question. And okay, if you want to learn more about this or think more about this, where can you find more information? So first, the paper is accessible and it's not very difficult to read. The proofs are intuitive and they're not technical, so you can find the paper online. Secondly, we have 2 different slide decks about this word available, both on Lige's website and on my website. And these slide decks have diagrams and pictures, so they're very nice and they're far more detailed than this talk. And lastly, we like emails very much, so please feel more than welcome to just drop us a line and chat about this. That's it. Thank you very much for tuning in.